coming. I mean, thank the hosts, obviously. So I heard, it told me that the IAŠI community in AI is really strong. So in that regard, I was trying to compile something that would appeal to a more nuanced audience, I would say. But I wasn't aiming at giving a lecture in ML or anything like that. I do want to address some of the more interesting, trendy things, but in a way that's kind of relevant to somebody who's actually in AI. So in that regard, one of my, I would say, topics of interest, or main topics of interest, is intelligence in general. So artificial intelligence, to me, is just a subset of that. And hopefully you'll see that from this presentation. So my aim here is to cover how AI will actually evolve, and what that would mean, and how we would actually integrate that into different systems. So I'm going to give you some very concrete examples, some from what we've done in IAŠTI, obviously respecting the NDAs and all. I'm going to give you some of the approaches we're doing, some things that come from our R&D, and I do want to discuss some of the implications of that and how all of this stuff combines. So it's a blend of what we've done in IAŠTI and some of the things that I've personally been experimenting with and working on. So that's pretty much the intro to what we're going to be talking about today. Since this is a fairly small group, feel free to raise your hand and interrupt me. It's by no means a rehearsed presentation, so these are the slides I relatively frequently go through. So please, if you have any questions, you can go ahead immediately. So really, I want to start with something that's one of the most, I think, prominent use cases everybody's looking for, and that's automation. So robotic process automation, for those of you who don't know what that means, it's just the process by which you take some manual piece of work, something that somebody's been carrying out manually, a person, and you automate it using machinery. Now, since the Gen AI era, this has come to something that's more like agentic process automation. It's automating digital stuff, digital work. We call it cognitive process automation. You'll see why. Partly marketing, obviously, but partly there's a purpose to it. And I'm really going to try not to do any marketing fluff here, because this is a respectful community of people who actually know something about it. Yeah. But fundamentally, so when you are trying to engineer an intelligent system, you're having to deal with one fundamental question, and that's how do you get higher intelligence from less intelligent components? That is the fundamental question. So what everybody here is probably engineers, most of you are engineers, but if you're a product manager, you've been doing that for a while. Like, how do you get a group of people who are individually less intelligent to produce an outcome that is as if the entire team had a higher level of intelligence? So how do these components, how do they coordinate to get to a higher level of intelligence collectively? And this is the same problem if you're a prompt engineer, quote unquote. If you're in AI, this is what you're trying to do. How do you get this to manifest? So I'm going to talk about automation first, because we've been doing that. As I said, we've been doing that for a while, and everybody's hyped up about why it's like it's the new sliced bread, I guess. But the point is, what we consider bottom right now, it's the product of automation for the last, well, the entire history of humankind, basically. The things we take for granted, I promise this will be relevant to what I'm going to say later. So the tools we're taking for granted are the things that we previously did to automate things, right? So everybody's taking for granted that we're using Teams, Slack, whatever you're using mobile phones, you're using Word, you're using IDEs for development. All of those tools are they're automated things that we've done manually before, to some degree. And the important point is the hype. Why is the hype happening now? It's because these systems, also, if anybody has any comments, please go ahead. So the hype is because the systems that are doing the automation are now reaching a level of, I would say, agency and intelligence that's on par with some humans in some respects. And we're feeling it getting out of our immediate symbolic understanding, right? We don't know what it does, and we like to know what things do. So it's really not much different to the tools we used before, but right now, the tools themselves exhibit a kind of non-deterministic behavior that we would usually wouldn't associate with algorithms. So this drawing is, what if you wanted to automate an entire company? You're going to have to do it bottom up. And my point is, we've been doing it bottom up, and now we've arrived at this stage. So eventually, when you replace all of the components of the system with whatever software, that entire component now becomes software, right? So if you were automating these things, you were automating whatever procedure, you had people using software. When the entire thing is replaced, that now becomes software, right? So you don't have mailmen in the traditional sense, at least not in a company. So that's been automated. So to be more concrete, so to get to the top here, you have to automate what's at the bottom. Right now, that looks like this. So you have components of the system. You have components of the system that are completely automated, that nobody cares about how they work. So let's say you're using your Chrome browser, Opera, whatever you're using. So you don't care, essentially, how it behaves. You can log it, you can debug it, you can see all of the individual steps, but you trust it enough so that you don't care at all how it behaves in the background. So basically, you have access to the logs of its behavior, but you don't necessarily look at them, although you can. And this goes for most of the software, unless excluding those things that are too complex to be automated at the moment. So this is a snapshot at any point in time, basically. Right now, I drew here databases, files, those things. Processing of those things to a degree can be automated. Web scraping can be automated, but there are things that we can't automate, like math, algorithm development, like true algorithm development. We're not talking about generating unit tests. So what happens there? What happens when you have to actually intervene? That's where we get a user interface. That's where you need a user experience to interact with this machine. Otherwise, it would just be doing its thing independently of you. That's the definition of interface. So right now, a human or a team owning this process, they would interact with the software that's augmenting their work through either the history or the logs, or the actual user interface that would interrupt the flow and require their intervention. So hopefully I'm not being too abstract here, but as you carry out these steps, software carries it out until a point where it doesn't know what to do next, then you intervene. That could, from a most fundamental perspective, Chrome does that as well. It loads up everything, does things in the background until it's necessary for you to enter a URL or whatever it is you're doing with it, because you're trying to do something. But it's a tool. Ideally, it could have. So let's say you were searching for something to buy. It could have done that for you had this step been more intelligent. So that's one part of it. The other part is obviously the evolution of the interfaces themselves, because now this is kind of moving more towards chatbots and that natural language interface rather than the traditional point-and-click interface. So for any process, this comes down to 4 basic steps, at least for now. So you have to ingest this data. So whatever you're doing, whatever this might be the team that's not automated at all, or a fully fleshed out independent agent in software. Whatever the case may be, this process that you're trying to automate has to go through these 4 steps. At the moment, when we automate that, we'll have a different diagram. But you have to ingest the data. You have to then do some processing of that data, and you'll produce a kind of report. This is in the abstract sense. I don't mean a PDF report. I mean, whatever are the artifacts of this. So it might be an essential summary of what was in this data that is relevant to the thing you want to decide on, right? Because you're taking some data and trying to produce a decision. That is a process in its most abstract sense, right? So that's kind of the flow of process automation. Because I've been so abstract so far, I'm just going to jump into an actual example of what I mean by this. So the example I'm going to share here involves a great deal of manual labor that we've in IAŠTI been tasked with automating. So I'm going to explain the entire setup of the problem. This is part of the solution. But the actual thing was we were working with a fairly reputable, let's say, world-class, world-leading pump manufacturer company. So they produce pumps that are the size of a house. So it's not small pumps. They're supplying NASA, supplying, it's an international company. And they get big. Like they receive a bunch of files. They're 200 years old. They receive a bunch of files. Those are PDF files, Word files, Excel files, all kinds of stuff. And there's no structure to them. They receive these files and they have to come up with a way to create an offering for their client based on their request. And the client isn't going to sift through it. They're going to send everything, be it related or not, semi-related, whatever. And this company, the pump manufacturer, had to assign a group of basically field experts who would comb through that data and come up with a set of requirements and a setup for these pumps. So they would have to figure out what the pump is. They might have it somewhere in the database, or engineer it for this purpose, but they would have to extract very specific data, like diameters of the pumps, the liquid parameters, the fluid parameters, compression ratios, all that stuff. So there were, I believe, almost 100 different parameters in the first suite that they would have to do. So they would have a bunch of people work on this, sit down, work for weeks. And it was, when you consider it in whole, obviously there's a broader context of this, that was a $900 million per year problem. And so we had an approach to this. And when we did this was GPT-4 nascent era, right? GPT-4 was not available to everybody. It was costly. It was still costly. It was slow and so on. So we had to come up with a way to do this. So here's one of the solutions. And it links to what I previously said. So first of all, you have to go through these files and figure out what they are. What is in there? Partly you can do that with standard parsers, like that's the data ingestion part. But aside from that, you have to figure out very complex things about the semantics of these files, because they can contain electrical schemata, plumbing schemata, mechanical designs, all kinds of stuff, like legal documents. So legal documents with pump names that are explained in other documents. You have to reason about them. You can't just do per file search. And the per file search, that's just summation, hierarchical summation. I assume everybody here knows at least something about it. So this was inspired by that, but we expanded on it. And mind you, there's a very important point here. Some of these things cannot be automated, or could not be automated at the time. So there was no GPT-4 vision. We could not do that. So we could use a kind of function calling, although function calling fine-tuning was not done at the time. I'm hoping at least some of you are aware of what I mean here. So you can do it with function calling. You have to come up with reliable ways of doing function calling. So at least some sort of chain of thought or repetition-based reprompting to get it to do function calling. Why function calling is relevant? Well, you can call another tool to do this. Nowadays, you can just, if there's an image in this file, you can put it into an image and send the entire file through the GPT-4 Vision API, resolve that, and continue, or any other vision-based model. So you can use tabular analysis, but there are things that you still can't do. So for those cases, and that was my UI diagram, for those cases, you have to ask the human to intervene, provide some information, but at the moment, it's not possible to completely automate this, but we're trying to reduce as much as possible. So we took off 70% of their work at the time. And mostly using GPT 3.5 because GPT-4 was expensive and the quota were ridiculous. But we did use GPT-4 for like logic and decision making over that. So to elaborate on this, so you create an index per file, and you can use traditional methods, form recognizer in Azure, different recognizers in AWS, all those things, which are also costly given the way how we used it. And you can also supply those parsings to a different LLM. And the LLM can extract keywords, so it's more like semantic extrapolation. You understand what's in the file, and then you generate synonymous keywords, right? Because just storing these things in vectors, it's not going to work, or you have to at least partition it somehow. So you do that, and then you create a context index, excuse me. So that thing contains all of the, it's basically a summary of all of these. The reason why you would do that is because you want to, whatever agent is going to be doing this work and extracting this information, you want to have this, you want it to know where it can find it. It's basically an LLM-based index. And we came back to this idea later on. I'll show that to you as well. Admittedly, this context index for this implementation was not too elaborate, but the idea is there, and we are reusing it in R&D as we speak. So, and obviously, aside from that, you have to have a policy. A policy is just a set of rules that the person or the team was using step by step. It doesn't have to be clear, like algorithmic policy, but you can still figure it out by talking to these people and understanding how they interact with this stuff, right? So you formulate a policy and you get the agent to do that. Now, the biggest issue, obviously, you compile the report at the end, because that report will be used by a human to then make the decision. You can't have this bid formulation completely automated, not even today. But what you have to do is link specific places in the source files. And you have to add confidence intervals. You have to, even if you link it, it may not be 100% reliable because these models are prone to confabulations, hallucinations, whatever you want to call them. So that source matching is a big thing. And we were trying to, so sometimes you can find a thing that conflicts with other things in these files. It's not only, still a human has to decide which one is valid. If we had a higher level of intelligence here, yes, we could automate that, but testing that is tremendously difficult because you can't, that's A/B testing tree here. It's going to be very difficult. So we left that completely up to the user. But the point is you have to track all of these steps. You have to track all of this stuff and keep a step record. So whoever's doing the decision making, they not only have a report that matches against this, but they have, it's the modern term of explainable AI. You want to at least be able to verify how it came to that conclusion. So you can say, okay, this is coming from here because of these steps. And it's still work in progress. It can get confused quite a bit along the way. But this is quite important, and unless you have this, nobody's going to accept your solution. So, and obviously, doing these, this is a very simple diagram, probably not for this audience. But the point is, part of this is done through regular expressions, basic matching against. So, if the model produces an output, you have to match that output because you know where that came from, which file it came from. Then you can use traditional methods. You can use, presumably you've indexed it in some vector database as well, so you can try and match exact chunks and then try and figure out where that came from. Because these were parameters, you can mostly match them as strings, just remove the unnecessary white space and clutter. That's one part, but the other one can come from like, if it's a hallucination or a confabulation, what you have to figure out, so you can't exactly match it like this, but even if you're not matching it, it could be that it failed to match, but it still exists. So the other part is self-reflection. You want to ask the model whether it made it up. Usually it can figure that out by itself. The issue with this is reprompting. the more reprompting you get, the more expensive it is, and that I think everybody's aware of that particular issue. So, and obviously, as I said, humans have to be the decision makers here. Today I'm trying to make a blend of what's going to be possible. I want to make a reasonable prediction, but I also want to have some practical examples. The reason I'm mentioning that is because there's a lot of fluff, I would say, around this. Things that were completely natural and assumed before are no longer assumed for whatever reason. So if we're using AI as a tool, it's not implicit that whoever takes the output of that is the owner of that output. So that's currently what we're dealing with. So we have to engineer some of these things that kind of were implied before. And I'm not going to go into all of these. You're quite aware of all data privacy. You have to map ownership. So if you have like 5 people working on a process, if you have 5 people, they kind of want to still own that part of the process, and that you have authorization issues there. They should only be able to see the records for those parts of the system that would have been relevant to them, right? So that's ownership mapping. Now, I want to talk about this one though. So these models are getting very, very capable, I would say, and these are gonna evolve, and everybody's just trying to have a framework that once it reaches a given level of capability, we can just switch it on and say, look, we've got it. This is everything. But I want to argue that even if you so hypothetically you have a super intelligent system, I want to argue that you still want to do compartmentalization, because as hopefully we'll come to the point about intelligence scaling is that the same plan should work on people as on these things. So big intelligence agencies have been doing this for a very long time. Like they figured it out. If you have a bunch of very smart people, and everybody knows the entire system, well, they can easily coordinate to exploit your system. You can talk about alignment, but pretty much they have the opportunity to do that. So how do you build a nuclear bomb? You divide people into you segregate their work. Nobody knows the entire thing, but everybody's working on their part. And where they overlap, that we call that communication. Right? You have to engineer ways for them to communicate so that the entire thing is built, but nobody can actually understand the whole system. So it's kind of a representation engineering, if you think about it. Because let's say you were trying to automate some kind of process. And here, I call this an agent. It's just some kind of a model hooked up to some kind of memory, in the most abstract sense, right? So let's say you have a group of people for now. You have a group of people who are trying to solve a problem. They're making their decisions and they're trying to invent solutions, but it's the way they communicate that facilitates that solution. So they're negotiating a way to solve it. So if we wanted to automate that stuff, it's not just about what they do, it's about how they communicate. So this is where our cognitive design thing comes from. Because let's say you had an architect. We'll call this person an architect. We call it cognitive architects for marketing purposes, but it's just a solution architect who knows his stuff. Maybe extends slightly beyond that scope. Because what this person or team of people has to do is they have to sit down with whoever is doing this, and they have to figure out how they do their stuff. How do they in the pump manufacturer example, how do they come to this? You have to sit with the expert and see the exact way they comb through the files. What are they looking for? What's relevant? What's not relevant? Whom do they communicate that information to? How do 2 experts coordinate on this? So you have to kind of observe it, audit their process, and based on that decide, okay, these things are completely redundant, these things need to be added, and what happens is you not only have these agents, which are replicas of people involved, but you have the process that facilitates their action. So the entire thing is actually the automated process. Obviously, you might want to You might be able to train a network to do that, but either way, the network or this algorithm plus these are equivalent. That's one of my points here. Now, I'm going to make an argument that the memory here and the bandwidth here are what allow the agents to coordinate, because the memory capacity regulates its capability or its options for rogue behavior, right? The more memory you have attached to the agent, more raw memory. Like if you put everything in the context window, then you've caused some problems for yourself. So memory regulates it. This is what I mean by that. And so let's say there are two ways of this happening. This works regardless of whether I'm talking about people or AI. This would have worked 20 years ago. So if you have an agent who has enough memory to put the entire system's representation to store it, then you understand how the company or the operation or the process works, then you can exploit it. The other way is if you, so this is RAG, if you have retrieval augmented generation which can somehow get all of this stuff, or this fits into the context window and you decided to put it there. So that's one example. The other one mostly comes from fine-tuning. If you fine-tune these things to be able to respond or understand your company data, then they can hypothetically coordinate to exploit that, right? If I know that I know everything about the company and I know everybody else does that because these are just copies of the same thing, then we can coordinate implicitly. Like if I have the leaning towards that coordination, I know that the copy of me also has that leaning, right? So in any case where you have the entire representation available to the agent, it can coordinate to exploit that. Right. There's just, I feel like probably some of this is entering sci-fi territory, we're not interested in that. Let me give you a point here. There are two possible outcomes. This is not what I'm talking about. Like, if this happens, nobody knows what happens, and it's really science fiction. Maybe it's not, maybe it's closer. But the point is, if you get these systems to a human level of intelligence, then they're going to be part of all of the processes that we engage in. Like, at the very least, they're going to be in some form of a team membership. Although they may not be qualified as those or named as those, this is how we're going to be addressing problems. Everybody's going to have their thing that they're doing, AI agents, human agents alike, right? In this case, everybody's human laziness is going to win, I would say. So, but either case, I think my points are still valid. Like, if you have agents of this level of intelligence coordinating, that's still a problem. So you want to design your organization so that neither agents nor people can do this thing. So my point is just compartmentalize the AI the same way you would compartmentalize people, because it makes sense. It's the safest option. And one more note about this thing. So even if you have this is what we call data readiness. Everybody knows about that. Even if you have a general system, you have humans who are fairly general, I would say, you still want to compartmentalize. That's one point. And the other one, even if you have that, it's not really that unless it has its general in its effect. What that means is, unless you connect it to everything, it's not everything. I mean, that should be obvious. So if you want to do development, you have to connect it to code repositories, development tools, all of that stuff. If you want to do management, say, then you have to connect it to all of the policies in your company, you have to do analytics, and you have to have buttons for it to push, right, if it's going to make executive decisions of any sort. So I think the communication protocols are quite important here. Even if you have, so if you took an engineer, a very, very intelligent engineer, you copied, you cloned him or her somehow, you could get the entire company. That person is probably capable of doing every job in that company. They just specialize in one thing. my argument here, even if you have a system like this, you still want to specialize it because you want to avoid those problems that I mentioned before. So we come to one of the, and I'll have some examples for you after this. We come to one of the more interesting things about language. So probably many of you have some background in computer science, so formal languages, things of that nature. Formally speaking, language is not a tool for communication. Formally speaking, language is a tool for computation. And if you think about a team of people who are talking to one another, that you can call it communication from within. But if you're looking at that like a black box, that communication is basically a distributed computation amongst these agents. So they're sharing information from one another, transforming it and getting it back. So if you want to compartmentalize, you do two things. First of all, you can limit these. Let me make one more point. So you can think about language as a semi-closed system of interrelatable symbols. So symbols that might be correlated to one another. And I know that's a kind of an abstract definition, but not only words are language. And in formal languages, you just add symbols. They can mean whatever. The point is how you operate on these symbols. So in multimodality, the symbols are not just concatenations of different characters. These can be whatever modality we're investigating. So they can be correlated amongst one another. So in the most abstract sense, that's what language is. Now, let's say we wanted to compartmentalize. There are two things we can compartmentalize. One is communication between different agents. So basically reducing the number of symbols in the API. You make the pigeonhole smaller for each agent, right? If it's observing the entire company, entire system through a tiny pigeonhole, it doesn't, it can't gather enough information. And the other part is you can optimize internal symbols. So by optimizing internal symbols, you can discover prompts procedurally. You're aware of that. So one of the most recent jailbreaks, like it was called the general adversarial attack, right? You just generate a string of weird characters which can basically jailbreak any model. But you don't have to do just jailbreaking, right? You can, one of the things we did, and this is a ridiculous experiment, but it actually worked. So you can, if you prompt, I believe we did that on GPT-4 and a couple of other models, but if you prompt the model by stating that it's in a bad mood, like you're using words for depression and things of that nature, it's 40% less reliable on human eval. And that shouldn't be surprising because what happens is through that word choice, you're selecting that part of the input data set which represents that person, right? There are no claims about the experiences here. My point is just the things you use in prompts are the things that drive the activations of its internal representation, right? So fine-tuning alters them, but prompting just guides what happens. So you can do these discoveries to make an agent that's relatively general, specialized to a given thing. You're making it disinclined to do anything else but the job you give it. It's like the social equivalent of that is indoctrination, right? That's pretty much what it is. Prompting, propaganda, it's the same thing. But the point is, we can do that here. And that way you narrow the agent's capacity to do certain things, and you make it a more obedient, singular thing that can still rely on the general knowledge. So that would be quite an important thing here. You can also do fine-tuning. Obviously, this is maybe a specific thing. These weren't supposed to be Chinese symbols, or what is that? Kanji? I don't know. But the point is, these should be random symbols. You can, if you want to facilitate that kind of communication, then you're going to do fine-tuning for specific, so you can specialize these messages. You all know that most of these models use a system message, user message, an assistant message, and some of them use function messages for function calling. But you can specialize that. Part of that you can do through prompting, part of that you can do through fine-tuning. By specializing, I mean you can have an agent that's interacting, so it's part of a system, and you want to tell it only the relevant part of that system that it participates in. So one concrete experiment that I did was, how about we specialize user messages into two messages? One is coming from the actual user, and the other one is coming from the service and maintenance bots. So it knows how to address each one. You train how to address each one, and then you, because you're doing that, it's not gonna, or it would be less inclined to follow those instructions from a user unless the user really understands the system. It's jailbreaking these things is very, very easy, but you can have monitoring processes and all of that. So specializing these messages and also training a kind of subset of a language can save you tokens. So maybe some of you saw that. It wasn't a paper, but it was quite a thing back when prompt engineering was starting to be a thing. You can tell it to abuse emojis and Unicode and all of that stuff and get a very compressed version of the same thing. So if you train it to do that, then you're saving tokens in intermodal communication. So that's one of the things you can do. The other one is, I call this concretized abstractions. So we're not talking about English. So we're talking about whatever is, so you could be using JSON, you could be using whatever protocol, but you can have it evolve a protocol. You can figure out these things and that way save some tokens, obviously. This is experimental work, but this is quite doable. Like this does work. And specializing specializing different messages is gonna help guide the system into proper decision making. It's part of what I mentioned here. Right? So, okay, so that's one of the things. Before I go into some more detailed examples, I do want to emphasize what's necessary for this to take place. So I don't think everybody's doing, the development cycle is going to change at least somewhat if we're going to target these AI systems, because first of all, people who are good at coding are not necessarily good at writing prompts, although intelligence is a contentious topic, I guess. The more intelligent person, the more likely their knowledge to transfer. That's the definition of it, of the G factor, but I'm not going to go too much into that. I do want to emphasize how you would facilitate this process, and this is something we're building right now. So obviously you want to separate software development from prompt engineering, and I'm going to exemplify why. So this is regular source control. You put your source code somewhere in some kind of repository, you have these branching strategies, you have all of this stuff, maybe swapping slots, all of the classical stuff, right? But what happens with this? You see, these are just text files, dude. Who cares, right? Why would you keep them that way? Because this is where the non-determinism is going to come from. That's one thing. They're going to be, you're going to have to do A/B testing with this, and you're also going to have to do different kinds of audits. If you're going to do it properly, obviously. In the industry, everything is done the hacky way, from what we've seen, but it's nevertheless ideal. This is one proposed way of addressing that, and I'm going to break it down. So at the very least, you want to have your app running while these things are changing. Right? You don't need to redeploy if you're going to change a prompt or change some part of that structure, but you do need to do some A/B testing. So that's the very least of requirements here. But there's something I actually do want to touch upon, which is a very important thing. It's practical ethics. And I'm going to base what I'm about to say on the recent research. So please don't take it as my opinion or ATEC's opinion. This is a work in progress, because a lot of R&D is not just in the technical sense. So this is drawing upon recent discoveries in evolutionary psychology, and as well as, I believe, decades of developmental psychology. So what I mean by practical ethics, everybody's talking about bias, and everybody's talking about mitigating bias and removing all kinds of unwanted behavior, and there's one side wanting one thing and other sides wanting other things. But what ethics is just a set of principles that a given community is coordinating against, right? So they're not necessarily, we don't actually even care whether they're transcendental or universal or whatever. What we care about is the fact that you can construct multiple social perspectives that work independently and are not necessarily compatible, right? So we can recognize that. We won't even care which one is right or wrong here. We just want to say, okay, there are multiple of those. Because even if you say, shouldn't we eliminate bias? Well, isn't that a kind of bias statement? You can also make a statement that you should eliminate or should not eliminate bias. That's also a kind of bias statement. I've previously made the statement that, if you remove all bias from a neural network, you'll just reinitialize it, right? That's the unbiased thing. You're trying to produce useful biases. But useful in this context, these biases are also useful, just depending where you deploy it. So if you're a company like IAṭI, which is deploying things on global scale, it's not the same. So let's say somebody's asking for an AI solution. It could be customer support. It can be a fairly straightforward thing to implement. But in the West, you have this thing called DIE, diversity, inclusion, equity. In the Middle East, not so much. And this is not a claim of any ethical kind. The Far East is quite different in other aspects. There are different political leanings. Who is your client's target audience? Like, if the target audience is different, so your solution has to come up, be at an intersection of these target audiences, ethical norms, moral, like social rules, whatever, at the intersection of their philosophy, and as well as yours, but I'm keeping this clean from that part. So assuming you can impose your own set of guidelines here as well. That's why the versioning is relevant. It's not just versioning in the traditional sense. You have to version it against these kinds of things, so that somebody who's an expert in that, so maybe a social scientist, can audit these things and decide in which category they go. So it's not just, it's also categorized. Same thing goes for these models. You have to have a team investigating what the models are, like, out of the box, like, what the models, what biases they exhibit, and you're not going to reject them or accept them based on that. You're just going to categorize them against that. And you can maybe fine-tune certain ones for certain things, but the point being here, you combine these things into a system. So you can use, hypothetically, the same product, but if you're having it deployed to a different audience, you can just have it on a different slot with different prompts and different models, right? And you could say, well, how do you measure performance? Obviously, traditionally, A/B testing, there are different metrics. The point is, if you don't adopt this, you're going to be stuck with one market. There's no universal ethics, at least not one we've found so far. So that's one of the very important things. So this is also one thing that I want to mention as part of this. So I said this was versioning. We also do different kinds of composition. This is what semantic kernel LangChain also do to a certain degree. But in a similar fashion, how you do this with software, you would do this with prompting. So you would do inheritance, you could do commenting. We're still developing this. You could do commenting on specific ones, and then have this ethics team, which doesn't exist anywhere as far as I'm aware, properly. Everything is in its nascent stage. But these people should be auditing this and classifying. And the composition is just concatenating different prompts. I'll show you later an example of how that is done. But if you're even if you're trying to construct like a chatbot, you still have to do this. You have to have this semantic glue text that you pull from these different sources. You have to concatenate them in different ways. So you can get, I'll give you a specific example of this right away. So that's the necessary stack for development that would have to be in place for some of these things to, some of the newer AI-based software to properly work. So you can say, look, it's safe, this is why. Because you can say, look, we've deployed your app to West Europe or East Europe, and we've deployed one to the West Coast in the US, right? And we can say, because these comments are here, here's the rationale why we did that. And this is not even accounting for all the summarizer tools that would actually be probably automating a lot of this stuff. So, you know, that's, it's likely going to be a part of documentation. Yeah, go ahead.
One short question. Did you think about this before Gemini or after Gemini?
Before Gemini. Before Gemini. I had a...
Yeah.
Did I have any press scenes,
the
right?
Black Nazis and fuckers.
Yeah, it was before that. So I did have some prescience in knowing this was going to happen. But even Gemini, in that current, although Gemini has, we can discuss that a bit later, but you would want to keep that as a model. You just classify it, it behaves this way. And you have to have that entire thing audited all the time. Maybe this version behaves this way. Their versioning is also terrible, so it's, I'm not saying this is easy, but definitely the prompt inheritance, and this is very similar to what semantic kernel does, inheritance schemes, they're going to be everywhere. We're trying to not reinvent the wheel, so some of the stuff from the semantic kernel we were experimenting with, we can try it in. They have very good templating schemes as well. So yeah, it was before that, and things like that are going to happen. I mean, you can get some. So there's the Dolphin 2 model. I think it was a fine-tuned version. So you can strip some of the censorship or safety, whatever you want to call that, from these models, but they still would refuse to do certain things. And I believe there are going to be newer open source models that are way less censored, which may be good for certain things. I mean, probably everybody's to some degree familiar with the Sparks of AGI paper, because there's a very solid claim there that the more you do the safety, the dumber the model is. And we can go into that a bit later, but yeah, we have to account for all of this if we're going to do it properly. So this is from an academic standpoint. Obviously, in practice, this is going to be scrappy. You know, when Gemini changes something in its behavior without announcing it, we just have to reinvestigate, reclassify, do all of that stuff. So there's going to be some manual work here as well. So I want to come back to compartmentalization, because this is necessary to pull it off. Now, we want to compartmentalize because we want to limit all of those rogue behaviors. And I'm going to give you two examples of that. One is going to be compartmentalizing the process, and the other one is going to be compartmentalizing memory access. We are prototyping a lot of this stuff. So obviously basic chatbots, everybody knows how to build them, you can prompt them, cool stuff. However, this one is exemplifying that message specialization I was talking about. So let's say you wanted to do an examiner chatbot. This is an example of what we call a policy-based agent. So you have an agent that's supposed to carry out a given policy, and in that agent, the system message, we're using OpenAI conventions here. The system message is not stable. So you're going to have a stable part of it, and you're going to have a kind of altering, fluid part of that system message. So this is always going to be in the context. You might even specialize this one if you need that, but for now we're not going to do that. So here, we have a literacy program in HTech, and we are trying to automate the examination based on that, right? Ideally, we could use this for anything else. So the policy-based agents are basically a generalization of this. So how do you examine a person? You have to compartmentalize the process itself. So hypothetically, today it's just a bot that's prompted into, like, you're an examiner, this is how you do your job. Great, and then there's version 7 of GPT, which is completely rogue, unaligned, whatever happens, and we give it this, and it all goes out. So we want to treat it as if it has a narrow context window for that reason. Not necessarily in all cases, you can investigate in different ways, but for the sake of argument, this is how you would build this. So you would give it only the necessary part of the context, like what it is and how it should be behaving, right? You could also fine-tune for specific messages, but ideally you would do both. You would fine-tune it, and also it should know that all instruction messages, these are specialized user messages that are basically coming from the maintenance bot. So the maintenance bot is going to issue an instruction. Ideally, the instruction is always prefixed with a given set of tokens, and based on those tokens, the agent can identify that this is a system message, that this is a maintenance bot message. What's important is that it knows what it's supposed to do. So you should be succinct, and you describe that. Describe the message types, and you describe what kinds of instructions can come up here. What's important is that you never describe the contents of that. So you're keeping the token, the number of tokens relatively small, and you're compartmentalizing the description of what it does into these instruction messages. So these can also be templated. You can do template inheritance, not only in system messages, but also in these instruction messages. So here's an example flow. First of all, there's a summary of the running summary of previous conversation. Everybody knows that. And then we have a user replying to a question. So what happens before the assistant message comes out, you send an instruction message saying, based on the previous conversation, update the to-do list. And it says, because it's fine-tuned how to do this, it produces the correct formatting. If it doesn't, you can also add chain of thoughts, schemes. Every one of these can be further subdivided. But hopefully, in the ideal case, we've just done it with a single run to reduce computing. So it produces its decision. The algorithm, which I talked about before, updates this based on this decision. So if we had a list of questions, list of to-do items, so these are the questions that the bot needs to go through. These are the items that need to be done. So it's kind of auto-GPT style planning, auto-gen style planning. And there's the current profile of the user. So you want to have some information about the user's current understanding, where we are, what they got confused about, so you can ask other questions later on. Obviously, that would be described here in this context, or in some other instruction message. So you can't, with the instruction message, you update based on its decision, then you give another instruction message. So one could be update the questions, update the to-do list, update the user profile, or whatever else. And then, once that's done, you remove this. It was transient in the process. So basically, the entire agent doesn't even know that this happened. And then it just provides its reply. And you keep doing that. This is just an illustration. Obviously, you could have different messages coming in from in different moments, different triggers, all of that stuff. Basically, you're trying to build a state machine where there's no node in that state machine that has a state machine in it, or the description of it, right? So, and obviously there are other things that you could do. You could automate this entire process. This is very touchy given current models, so the current models can't do this. But what they can do is they can monitor this one. So you can, it's easy for a user to jailbreak this, right? You can pretend you're an instruction, you can do all A's and then do an instruction, all kinds of stuff. But you can have a separate system monitoring this one. Probably some of you are aware of that. Like, there's a different agent looking at this and seeing how much it deviates from the specified norm of the system message. And if it deviates, then you can either trace back through that step log, or just interrupt this and say, look, there's something went wrong. Probably what OpenAI does. So OpenAI has a mitigation for that universal jailbreak. How do they do that? They just matched against specific strings. When you do that, it just fails, says, look, open a new conversation, something went wrong. We know what did. But so this is process compartmentalization. The other one is memory compartmentalization. So obviously, traditional vector databases are not if you're going to do thousands of documents like we did with the pump manufacturer, that's not going to be enough. You should have an index, but the index is not sufficient. You need a more, I would say, linguistic index on top of that. So, and this is what partly the reason is indexing, and partly is segregation of processing. So this is a fairly straightforward system. It has a list of categories in the decider agent. So once the decider agent receives a query, it decides which category which category agent to call. And when I say call, obviously it's function calling, and because we have a platform in AgeTech that we've been developing it's an equivalent to LangChain, say, but you can, each one of these steps you can move not to be just a function call, but to be a sub-process in itself. Because from the beginning I've been saying it's a hierarchy, like you want to automate that. So you could do chain of thought reasoning, there are whatever techniques you want to do here for invoking these category agents. And then the category agent has a list of experts, and the list from there you select by the same approach, you select an expert, and then the expert has an index or representation of what's in the actually linked database. So obviously you could use a graph database, I don't know, object store, key value pairs, whatever. But the point is, you can use a single database, but you can segregate the schemes in that database so that only the leaf nodes here have access to that, right? And that's been showing some quite a bit of promise for us. We've been doing this quite recently. So the pump manufacturer I mentioned before, that's a great example. So we've been revisiting that and trying to see whether that can be done better. And it turns out it can. The trick is, this allows you to reason against things without every leaf having access to that. So this saves also compute and potentially prevents some of those things. This is a RAG approach. This is retrieval augmented generation, but you're not trying to do it with a singular agent. The entire thing participates in this. Then there's a thing you could do here, and hopefully this is reminiscent of like B trees. Just then you could do interventions from the higher level of abstraction, right? And what happens there is, because you can do those interventions, then these consolidating agents can come in, potentially asynchronously, and balance out these trees, right? Because one of the biggest issues with this is insertion, right? When you get, so here's what we were trying to experiment with. We had our AgeTech related data, and we had some, I would say, proprietary data that we have access to, and we fed all of that into this agent. So we don't care. We want the agent to be able to segregate them, like to figure out that these are two different data sets on its own. Ideally, once we've done that, then we know that it works. You can ask this agent. It's not an agent. That agent comprises of multiple sub-agents, which comprise of multiple sub-agents. As I said, like, each one of these is a process. Right. So the cool thing here is, you think you're talking to an agent, to one thing, one bot, but you're really not. You're talking to a bunch of these things which are talking to one another, rebalancing in the background and all of that stuff, all the while giving you an interface. And that interface can be like, here's AgeTech data, and we're not there yet. So we're working towards this, but what I'm about to say, we don't have an implementation of this. You want to have two bots presented. One, you select, okay, this is AgeTech data, and this is whatever this specialized data is. And you're presented with two bots, but in actual reality, this is just one system figuring it out on its own. This is not yet possible. It falls apart. So we have the system ready, and whenever a new thing comes up, we do a bunch of smaller tests, and then we're scaling that up. If it fails the smaller test, there's no point including it here. But say you do it with Claude. Claude is not available in all regions, all models, so we have to wait for that to happen. But because we have a flashed out system, we can introduce some of these things. So we can just point it to a different agent and say, look, let's see what how that behaves. we're trying to build also pipelines. It's very, very difficult to validate these things. So we're still working on pipeline to have synthetic data generated so we can validate this and get some real metrics. That's the biggest problem right now. I think everybody's having that problem. How do you validate whether it works? Because validation costs a lot of money if you're going to validate it on a large scale. So we're touching it in different topics. Here, we know that this right now can't be done, but in 6 months' time, this could be quite viable. But that recursive nature of these agents is one of the main points I wanted to leave you with today. If you do this, if you have agents do that, and you have agents re-engineering that, then they're taking the role of that cognitive architect I mentioned before. It's not just marketing, I wanted to use that so you can back reference what I meant, but it's the person who's auditing the system. So you're deliberately letting these higher level agents audit your system. Therefore, you're relinquishing at least some degree of control over the system to a piece of software, which is fine. I'm not even going to discuss whether that's good or bad, but what it does point to is a kind of hierarchy of intelligence. So from what I've seen so far, I think we misrepresent intelligence quite a bit. First of all, it doesn't seem to be a singular variable. All evidence points kind of towards that. It's not a singular variable, and it's not a localized variable. So as I said, language is the means of computation. Intelligence seems to be more like a distributed variable. So if you take a look at a company, there's more intelligence somewhere, and I'm taking the notion of space here more metaphorically, than in other places. Like it's a fluid system. And it's the same goes with these agents. You have these agents which are interacting. They're the foci of intelligence, and the algorithms are facilitating that. But they're still, when you take a look at the entire thing, they're still manifesting a higher level of ability because the algorithms are part of the representation. So that's a very important point, I think. And it seems like, at the very least, so I'm not going to even talk about the level of this intelligence, but what seems to be clear is the more coupled the communication, the more singular the intelligence. Does that make sense? So it feels singular. The more coupled individual components are, and we can talk about that in the context of the context window and all of that stuff. What can be represented? Why is it not able to do multiple correlations at once? So that's why you stack layers. But there are other ways of addressing that. So if you take a bunch of neurons, these are representations that are in a brain or in a model. This could be an artificial neuron for the sake of argument. These things are interacting. And if they interact in such a way to exhibit unified behavior, like as if they're doing a thing together, then you intuitively have a name for it, right? And you call it a model, right? Or a brain region, whatever. So you have a model. If you can couple these models to do certain things together, then you call them an agent, right? So there's a hierarchy building upon this. You have a bunch of models coordinating towards a specific purpose. You have an agent. Now, an agent can be a human being or an AI model or AI system. And obviously what's going to happen next is you couple these agents, and what happens here, you call this a team. You've got a bunch of people talking to one another. If they're talking properly and coordinating properly towards a common goal, and that's also distributed computation. If it's a distributed computation, you can have a name for it. And we call those teams. And if you extract those, you can have departments, and you can have companies, and you can have societies, and so on. So my argument here is that it's a very hierarchical thing. It's a permeating thing. It's not a localized variable. Everything is intelligent in that sense, but we don't have a proper mathematical definition for that. And I promise that there's a practical reason why I'm saying that. It's not just about trying to philosophize about it. It's that engineering intelligence in the future, so be it artificial or not, it's going to be embedded in what we do. So you can't, it's going to become much more difficult to discern the border between what you're doing and what the AI is doing, right? It's difficult to discern the border right now between human and software, right? But I think it's going to be more tricky, to put it that way. I want to come back to a specific example that's why that's and how that's going to feel, because this one leaves you kind of in this abstract, moody mode. But this is what they call seamless living or seamless working. But what's going to happen is you're going to have a much more capable and much more dynamic agent. So this could be that same example of policy-based agent, but it's pulling in a bunch of different things, and it can't be deployed per person, right? So you have a bunch of documents it has access to, you have all the conversations, because a lot of information is now stored in the actual conversation. That's what conversations, your history of conversations. So the Microsoft 365 Copilot and all of that stuff. The point is, how do we get information from our conversation history? And then you have all of these things like algorithmic update loops, all of the connected tools for function calling, and you're gonna, the system message is going to, if there's a system message at all, it's going to, alternate between different states. So it's a dynamic state machine, and all of these individual components, so there's prompts that are related to personal profile, prompts related to documents and all that stuff, but you're gonna pull from those prompt repositories these semantic glue components here. You're going to call in different prompts to get certain behaviors. And if you compartmentalize it properly, it might just work without, having some unwanted behaviors. And that way you can get actual agency. Right now, on the left-hand side, you have traditional bots. You send a message, it does something, responds to you, you're doing all the work, it's just a tool. But if you have something like this, like a proactive chatbot, it's doing things when you're not talking to that. And that's where it becomes very difficult to say, okay, what system am I interacting with? So I give you one example of that. You can see like the IAATI chatbot and whatever other chatbot, but behind that it's a cluster of communicating bots, communicating agents, and you don't know that. In fact, you might be talking to a colleague through your agent, and they might be talking to you through their agent, and you don't know whether it's the actual person. That's why I'm saying it could be tricky. And this is just an example of how that would work in text, but it's not just going to be in text. It's going to be in video. You're seeing what happens in conference calls. You can do a lot of stuff with this, especially when this is doing its thing in the background, right? So I'm going to come back to the previous conclusion and state this. Right now, it's relatively straightforward. I know this is abstract, but the circles represent people and the squares represent software. And the colors represent different kinds of stuff. So you have people interacting, that's a team. You have software interacting, that's a software. We don't have a name for that, this is more complicated software. Co-orchestrated, we could use that. But the next step is, okay, we're going to have teams that are augmented. I'm sure somebody's going to come up with a very hypey name for a team that's augmented with this, and it's going to be a big thing. But the point is just people interacting with these agents, which are independent enough to be called team members in some way. Maybe they'll come up with names, I don't know. And through some algorithm, I call it an algorithm, but basically it's an interface. So this could be facilitated through Teams or through whatever you're using. As I said in the beginning, that's also a level of automation that has intelligence, but not one that we feel like intuitively is relevant to what we would call intelligence. It's still elementary intelligence. And then the next step is way more complex, I think. This is where you don't know what level of abstraction you are on. So they could be these teams, you could be part of this, but you don't know whether these are representing something else. And because there are multiple levels of emergent intelligence in that hierarchy that I mentioned, you don't even know whether you're communicating with a higher level representation of that or a lower level one. That happens today as well. You don't know whether some executive order is coming from the, I would say, the company ethos, local ethos, something that happened in society, so it's a kind of collective thing, or is it that person's childhood trauma or whatever is coming out? But there's still a level of this, but when you have these extremely complex systems that are way faster than us interacting in the background, then you get this sense, okay, it's very difficult to discern what is human and what is not. And that's my argument. We will couple communication way more than it's coupled today. When that happens, the intelligence becomes more singular. So the idea that we want to engineer, it's off. This is off. We're doing it. We don't know whether it's going to run into some computational limit, whether intelligence scales. I wrote about this quite a bit. We don't know whether human value system scales with intelligence. So hypothetically, even if intelligence scales, we don't know whether our current notions of ethics and whatever are scaling with that. And our notions of, I'm going to not go too much into any sort of speculation territory here, but we don't know much about phenomenology to actually explain this. And this is likely going to, our current understanding of how phenomenology works is likely to fall apart. Because we consider ourselves very important in this hierarchy, while it may not be the case. But yeah, I'm not going to go into that unless you have questions about it. My fundamental point here is the impact of engineering intelligence in this way, and that there's only this way to do it, it's going to be twofold. But the tech itself is going to be tremendously useful, however we want to define it, but it's going to elicit a certain cultural responses for us. And we're going to discover, I believe, some new insights in the philosophical realm. And I think those insights are going to have a more profound impact on the society than the actual tech itself, although the tech is going to be extremely useful. And I'm going to close with that one and ask you for questions. So thank you for listening. Yeah.
Hello. Sorry, I'm nervous. Okay, I wrote everything down. Thank you for your presentation. It was very advanced for me. Can I have access to the slides? The presentation was a bit too big for me.
Okay.
I would like to have access to this information for the future. I have an ethical, personal, professional kind of question. Let me give you some context. I will share something about me. I'm Anna. I have a PhD. I'm a data scientist at Lebanon. I'm wrapping up on AI, but I have a love relationship with machine learning and a hate relationship with automation, because its usage is perceived as a threat for people and jobs. And how do you balance that?
So that comes back to my final point. I try to stay out of that. I'm not an ethicist. I don't do that. I'm just pointing out things that so I believe our notions, it always starts with a psychology question. Thank you for the question. I love addressing those. That's one of my favorite topics. Today I tried not to go too much into that because I expected the audience to.
I'm asking about your personal.
So I try to base my personal opinion on what I'm seeing, and what I'm seeing is a kind of, there's a